Let's get some practice solving dynamics problems. So here we're just going to be focusing on working with Newton's second law. We're always going to draw a free body diagram. We're going to label all the forces in our free body diagram. We will write a net force equation by adding together all the forces. And remember, when we add them together, we don't just add their magnitudes. We have to look at the direction that the forces are acting on the object and add them together correctly. That means adding all the x components together and separately then adding all the y components together. Then we'll use Newton's second law, F net equals ma, to solve for whatever is unknown. And here it is. Here's Newton's second law broken down into components. So the net force in the x direction equals m times the acceleration in the x direction. The net force in the y direction equals m times the acceleration in the y direction. Here it is written in words. Okay. So let's start with some simple problems. We have an anchor hanging at rest from a boat by a chain. The anchor has a mass of 50 kilograms, and I want to know what is the tension in the chain. So press pause and take some time to work through this, and then press play when you're ready to go through it with me. So I'm going to start with my free body diagram. The only forces acting on this object are tension and gravity. Tension's pulling up, gravity's pulling down. One thing I'm going to start doing, because we have, the force of gravity is equal to m times g, where g on Earth is 9.8. And then we also have separately Newton's second law, which says the net force equals m times a. I don't want the m times a to get confused with this m times g. So what I'm going to start doing is I'm always just going to remind myself, what is the force of gravity? It's equal to m times g, always. That is what the force of gravity is on an object. I just want to have that nice and clear right here in my free body diagram so I don't get confused later. So there's my free body diagram. And now I can look at the net force in the y direction because all my forces are in the y direction. So these numbers here are just magnitudes. T is just a magnitude, it's just a number. mg, that's just the mass times the gravity, that's just a number. When I'm going to add my vectors together, but because my force of gravity is pointing in the negative y direction, I need to subtract whatever number that is. Because to add t and the force of gravity correctly, t has to be a positive number and the force of gravity should be a negative number. And the force of gravity is always equal to m times g. So my net force in the y direction is equal to t minus mg. The net force in my y direction is always equal to my mass times my acceleration in the y direction. That's Newton's second law. So I set those two things equal, and I have t minus mg equals m times a. And now I can plug in all the values that I know. And I find that the tension is equal to 490 newtons. The tension is equal to this weight, this force of gravity. So let's look at this problem now. Press pause and work through it. As you're working through it, pay attention to what is similar and what is different about the previous example. Okay, so when we look through this, the only difference is that now the anchor is moving upwards. But it's moving up at a constant speed. That means the acceleration is still 0, just like it was in the previous example. My free body diagram does not change. My net force in the y direction has not changed. This is not changed. This is always true. But most specifically, because the acceleration is still 0, the tension in the chain is exactly the same as the previous example. Everything that we're looking at here is exactly the same as in the previous example, because when we're looking at forces, all we care about is what is the acceleration of the object, not what is the velocity of the object. So whether the anchor is hanging at rest or it's moving at a constant speed, in terms of what's happening to the forces, those are identical cases. So here's another example. Press pause and work through this one. Okay, the only difference in this case is that now when I go through, my acceleration is not 0 anymore. Now it's 2. And that changes. That means that the tension in the chain is bigger. Why is the tension in the chain bigger? Because the chain has to pull up with more force in order to get that anchor to accelerate upwards. Okay? Let's do another one. Okay, so press pause, work through this. Okay, let's go through it together. The only difference here is now we're on the moon. Does that change anything about my free body diagram? Well, it means that the force of gravity is now the force of gravity on the moon. It's going to be equal to m times g on the moon. G is 9.8 when we're on Earth. When we're on the moon, it's 1.6. My net force in the y direction is still the same as before. The net force in the y direction is always equal to the mass times the acceleration in the y direction, so I can set those two things equal. And now when I plug in my values, I'm going to plug in that G of the moon is 1.6, and I find that my tension is 180 newtons in this case.